What is the smallest near-term mass driver we could actually build on the moon? How long is it? How many tons does it weigh? What does it take to actually build it? Now, for the first time, we actually have the baselines needed to do it. We know the destination, the launch site, the required ejection velocity, the rocket delta V, the thrust to weight ratio, and a defensible first estimate for pod size and throughput. We ran more than 720 hours of orbital simulations, optimized multi-burn trajectories through the Earth-Moon system, searched for a continuously accessible route to low Earth orbit, combined 9 lunar resource maps with terrain data to choose a launch site, and worked backwards from orbital requirements to size the rockets and the mass driver itself. The result is a candidate system with a specific destination, a specific launch site, defined delta V and thrust requirements, and a first estimate of the power, cadence, payload size, and throughput needed to continuously move lunar material into Earth orbit using a first-generation lunar mass driver. And we've made the data and code behind all of this open source and available on GitHub, so you can access it, inspect it, and run it yourself right now. So, okay, here's the question that began this project. What is the smallest near-term mass driver on the moon? Like, what does it look like? What are its actual design parameters? How long is it? How many tons is it, approximately? What is its peak and average power? What are its thermal properties and cadence? And what is its governing constraint? And what I mean by governing constraint is, what is the bottleneck that sets its minimum design parameters? Or maximum design parameters? Like, what is the hardest thing that has to be solved in order to build this thing? And we can actually answer that question now. The governing constraint, the hardest limiting factor of the mass driver, is power. Power is a measure of work per second, and power tells you how much your hardware has to actually survive. The flywheels, capacitors, batteries, buswork, switches, rails, contacts, insulation, heat rejection, fault protection, current paths, and the electromagnetic forces trying to tear the system apart are all determined by power, not total energy. A gigawatt does not mean we need a gigawatt-sized solar farm. The energy can be accumulated slowly and discharged quickly, but the discharge path, that hardware that turns energy into work on the payload itself, the mass driver itself, has to survive whatever peak power is. So I like to think of peak power as a sort of measurement of complexity and involvement and intensity. It gives the qualitative vibes of how easy or hard the system is going to be to construct. It is sort of a heuristic for probing scale. To see this, let's do a quick sensitivity sweep, and please bear with me. So to start, if we hold acceleration constant, then the force is constant, but the power is not, because power is force times velocity, and velocity keeps rising, so power peaks at the muzzle right before the payload exits. Assuming a constant acceleration launch, that peak power is mass times acceleration squared times time, and the average power is half of that. And the track length is velocity squared divided by 2 times acceleration. If we assume a fixed target velocity of 2.54 kilometers a second, then we can make a table showing the lengths and peak power at different accelerations for 10, 1, and 0.1 ton payloads. The first thing that stands out is the insane length requirements of the 1G cases. At over 322 kilometers, we can basically ignore them on the grounds of being unrealistic and just look at the more palatable 10G 32 kilometer case. Though these have higher power requirements, as you can see, peak power is in the gigawatt range for 10 tons, hundreds of megawatt range for 1 ton, and tens of megawatts for hundreds of kilograms. 254 megawatts of peak power for 1 ton at 100 meters a second acceleration isn't that bad. It's ambitious but doable, except this isn't the real number because, unfortunately, this table I've been showing is for the ideal case, with no efficiency loss accounted for, but real systems have efficiency losses. So here is the table at 50% efficiency, and 50% is still exceptionally generous, as most of the figures I've seen for non-superconducting mass drivers fall in around the 30% efficiency mark, and at 30% efficiency, the table gets a lot more damning. At 100 meters a second of acceleration, will require about 850 megawatts of peak power to launch a single ton. For reference, that's enough electricity for roughly 60,000 people at US consumption levels. So basically a citywide grid worth of electricity directed into a single contact point or coil. Now, you might argue that this is peak power, and peak power only happens at the very end of the shot, and that is true. But this isn't like electronic warfare or nuclear tech applications where a gigawatt pulse might last a millionth of a second. At 100 meters a second, the shot lasts about 25 seconds, which means the launcher spins about 12.5 seconds above average power on its way to peak, and spends the final second or so very close to peak. So focusing on peak power makes sense, as it is what the hardware ultimately has to survive for relatively meaningful amounts of time. So power is the governing constraint, and it is a problem. But we have two solutions to reduce it. We can either lower the acceleration and thus increase the length of the track, or we can lower the mass per shot by shrinking the size of the mass driver rocket pods. And long story short, shrinking the size of the rocket pod to lower mass is the better option of the two, because decreasing acceleration will increase the size of the mass driver, since track length scales roughly as 1 over acceleration. So you are gaining lower peak power, but paying for it with more track length, which means more refined materials for rails and supports and power electronics and more terrain preparation and everything else. You turn the power problem into an enormous civil engineering distance problem, so you're sort of trading one complexity for another. On the other hand, if you lower the size of the rocket pod, you can lower peak power without making the launcher longer, and in fact the entire launcher can get smaller. Less power for a smaller payload means smaller rails and structure, less power electronics and radiators and plumbing, while keeping distance fixed. But this comes at the cost of the economics. Smaller rocket pods means less throughput per hour, unless we don't shrink the mass driver with the pod, because then we can fire more often to keep up the same throughput. For you see, a mass driver is really sized around thermal control. The rail segments or coils have to be large enough to not melt at any given current. That's what we mean by our hardware has to survive a certain amount of power, and thus how power dictates the size and why it's a governing constraint. Too much power just simply melts these things. So the consequence of power is thermal, and cooling with relation to power is what determines the size of the mass driver, the amount of tons of material it is made of. But this isn't determined by cooling perfectly back to ambient between shots, as that would take way too long. Rather, it is sized around steady state operation, how much heat is deposited per shot versus how much heat the rails reject between shots. Since temperature radiates to the fourth power, the hotter something gets, the hotter it radiates, so we reach a point where tempo determines temperature, where our material limits don't determine whether or not we can fire a round off without melting, but rather the rate at which we can fire rounds, our tempo or frequency, and this is the same with things like a machine gun or an internal combustion engine. It isn't designed to survive one shot, it's designed to survive firing off 1,000 shots per minute for 10 hours or whatever. It is designed to heat up to 300 degrees Celsius and operate there, not at room temperature after a single shot. So if a smaller pod deposits less heat per shot, then we can fire more often and keep the same output, keep the same economics for the same thermal profile, like a machine gun firing smaller bullets faster or big huge bullets slower. If we size our mass driver for throughput, and let's say for an output of 1 ton per hour, we could fire a single 1 ton pod once per hour, or we could accomplish the same economics by firing 10 100 kilogram pods in an hour, and the thermal profile, and therefore materials required to build the mass driver, remains the same size, but the advantage of firing a 100 kilogram pod once every 6 minutes is that each launch has 1/10 the peak power demand, so our power electronics can be made more easily. That is the big takeaway. Smaller and quicker is better than bigger and slower, because peak power is able to be reduced for the same economic throughput and mass driver size and length. But if going smaller and faster is better, then the next question becomes, well, how small can we actually go? Can we shoot 10,000 bullet-sized mini rockets a minute in a constant stream? Or 100,000 sand grain-sized micro rockets? Can we approach the quantum scale? Obviously that's ridiculous, but why, and where do you draw the line? And we can get an intuition by trying to imagine how one would build a sand grain-sized rocket. So we can see there is obviously some limit to how small we can go, because every rocket pod has overhead mass that does not scale away as we butt up against material property limits. But to truly know how small we can go, we need to know the orbital requirements. This is because in order to design, and therefore size a rocket, at the very top you need to know two first-order mission characterizing numbers: the required rocket delta V and the required thrust-to-weight ratio. The first, delta V, mostly determines the propellant mass fraction, and the relationship is given by the rocket equation, written here in its delta V form, where m0 is the initial wet mass before the burn, and m of f is the final mass after the burn. That final mass is basically just the dry mass. As we can see, delta V is proportional to the natural log of mass ratio. So reducing the required delta V does not shrink the rocket linearly, it reduces the required propellant through an exponential improvement in the wet mass to final mass ratio, which then cascades into smaller tanks, casing, structure, and everything else the rocket pod has to carry. And then the second mission characterizing figure, thrust to weight ratio, can be thought of as the acceleration requirement, how fast it needs to spin that delta V, or rather the mass flow rate the rocket needs to be capable of. And it mostly determines what kind of engine is needed, which is mass flow rate, engine size, tank pressurization, structural loads, and thermal demands, that sort of stuff. Of course, these are not the only numbers needed to fully design a rocket. We still need to know things like propellant choice and materials like aluminum or iron or titanium or steel, but all of those things live downstream of delta V and thrust to weight ratio, and are mostly going to be dictated by our ISRU bill of materials. And because delta V and thrust to weight depend on the orbital trajectory, the journey itself, they therefore depend on the answers to a new set of questions, which is, well, where does the rocket actually start from? Like, where is the mass driver launching them from on the moon? And where are they traveling to? Like, what is their final destination? And for reasons that I hope should be self-evident, at the final destination of these rocket pods, there should be located a second major infrastructure project, that which receives the mass driven by the mass driver and processes it. For simplicity's sake, we'll just call this the orbital depot. It's where the lunar launched mass is, at the very least, stowed, but also likely refined and processed as well. And this orbital depot is just as important in the whole lunar mass supply chain as the mass driver itself. It doesn't have to be complex at first, just a laydown yard in orbit. It might even be constructed using ships retrofitted into wet workshops and things like that. This gives us something to build from, and we can evolve it as we expand and scale up our capacity. It is the foundation upon which we will build out the rest of our orbital industry. But the question is, where do we put it? Like, where do we actually locate it in Earth's orbit? And then, since smaller but faster launched rockets is better in terms of power systems, as we've just established, we can add another question, which is that of access windows. Since the Earth and the Moon are both revolving around the Earth-Moon barycenter, which makes transits through the Earth-Moon orbital system more complex than the regular elliptical Keplerian orbits we're familiar with from high school, this introduces the question of whether it's always possible for mass driver launched rockets to reach their orbits, or are there limited flight windows that we have to fly through? Can we design a collection of transits, a transit constellation, such that we could potentially reach our receiving station no matter what? In other words, is it possible to build a constant access mass driver? Or are there only certain windows, certain flight times for any given start point to a given endpoint? And if there are windows, how tight are they? Once a day, or once a year, or once a decade? Do we need to build multiple mass drivers across multiple lunar locations to even have a shot at making this work economically? Because if so, then that's very bad news, as even one of those assets will cost many billions and take an exceptionally long time to build. And so we can see how these orbital dynamics questions actually dictate everything downstream of them, as the requirements for what the rocket pod has to do in orbit dictates the size of the actual rocket pod itself. And the size of the rocket pod itself dictates the actual size of the mass driver, because it determines how much work it has to do. It determines peak power. So all those questions we asked at the beginning about the mass driver, like how long is it, how many tons it is, what is its peak and average power, what are its thermal properties and cadence, what is its governing constraint, all of those technical specifications are located downstream from the orbital dynamics questions that we need to answer. So we need to work backwards from delivery to muzzle velocity. The destination is the place where we need to begin in order to begin designing a mass driver. And with that, I will end this beginning. And fortunately, we have lots of open questions for a good YouTuber to draw out for as long as possible to maximize retention as much as possible. Unfortunately for YouTube's ad revenue though, I'm not a good YouTuber. I mean, just look at how ridiculously long and convoluted this intro has been. So here are all the answers up front. How did we get these answers to those questions? Well, now that's a good question. The answer is, we ran restricted 3-body multi-burn orbital simulations on 64 gigabytes of RAM for over 720 hours to simulate and optimize different trajectories from the moon to low Earth orbit. Now, of course, returning viewers might be wondering why we are presenting new simulation results, despite the fact that just a few months ago I released a quite big video presenting the results of simulations of the same nature. These new simulations are much more advanced. They account for the major oversights in the older version, and they include multi-burn trajectories, meaning the rocket pods are no longer limited to one corrective maneuver. They can perform several burns during transit, whether that is done with restartable propulsion, multiple discrete motors, or some combination of larger burns and smaller trim maneuvers. This gives us far more control over the trajectory and a much better picture of how real lunar to low Earth orbit transfers might behave. Though these new sims aren't perfect, and it's worth noting that we have left out some details in these new simulations as well, but we now understand the problem well enough through reading and designing simulations to say these details are minor enough so as not to affect the validity of the current sims so long as we accept multi-burn. Also, the older simulations were not for nothing, they taught us a ton, and some ideas presented in that prior video are still valid and carry over, and those conclusions are covered in depth in the previous video, but since they are so important, I think we should still briefly revisit the logic underpinning them. First, the need for controlled payloads, what we might call mass driver rockets or rocket pods. With a mass driver, you cannot just shoot dumb rocks into space and expect them to arrive anywhere in a circular, stable, aligned orbit. Real payloads have to do cleanup work, raise periapsy and circularize, correct attitude and navigation errors, and make whatever small plane and timing adjustments are needed, because a surface launch can only put you on an initial trajectory, not deliver a final operational orbit by itself. In other words, every payload needs a rocket thruster capable of performing the careful maneuvering required to reach and rendezvous in low Earth orbit, regardless of the initial orbital conditions. These rocket pods can be relatively simple, they just need a single burn to slow down, which means we can use solid or hybrid rocket propellants entirely sourced on the moon, and they don't need control surfaces or landing gear or nose cones because they'll never enter an atmosphere. We typically associate rockets with high complexity, and rocket engines are always shown as Lovecraftian messes of plumbing, turbopumps, and cables, but there's actually a very wide range of complexity when it comes to rocket engines, what we might call the firework to full flow staged combustion scale. For these rocket pods, we're talking about engines that are much closer to the firework end of the scale, maybe something like the V-2 rocket bombs used in World War II, or the solid rocket space shuttle boosters, than current Raptor engines. Actually simpler than the V2 or shuttle booster, since again, we don't need to worry about anything atmosphere related, as a lot of this huge complexity comes from all the difficulties imposed having to negotiate an atmosphere which is highly corrosive, unpredictable, turbulent, and imposes a huge amount of form factor and thrust constraints on rocketry. Our lunar-made rocket pods can have minimal moving parts, mainly being controlled more with power electronics, which can be radically inexpensive and simpler to design, build, and verify. And we should care about simplicity specifically for disassembly, because once these rocket pods reach the orbital depot and offload their cargo, we'll be left with what is essentially a spent casing, and we'll want to recycle these at the orbital depot because these casings are themselves refined, usable mass, likely aluminum or iron. So we'll probably need meltdown hardware at the station, and this has another implication too, which is that whatever the casing or rocket pod body is made of will be the thing we ship the most of. So if it is aluminum, we're going to be sending tons and tons of aluminum just to deliver other things. And in line with that, the next conclusion from the older video is that of the location of the orbital depot these pods are arriving at, which is the answer to the whole question of where in orbit do we put the orbital depot, which is the destination question. L5 is likely the best place for mega construction, but right now there is no market for such things. That comes later. Today the market exists in low and medium, and to some extent geostationary orbit. This is where people are willing right now to pay for mass, for propellant, for radiation shielding, for scaffolding and structures, for hardware. This is where the satellites and stations are, the constellations, the existing and planned projects. And so it's my opinion that low Earth orbit is where our target destination should be, because it is where the customers and demand exist today. It's worth noting though that this market is almost exclusively communications and information based, and that's largely due to the constraints imposed on mass to orbit cost. But with thousands of tons of mass in orbit to play with, we can do these things, which I'm just going to list on screen for time's sake. But we can't just say low Earth orbit. Low Earth orbit is a big place, so we have to define exactly where in low Earth orbit we should aim for. And we picked low Earth orbit because we said that's where the demand is, so where in low Earth orbit are the customers? Well, they're all mostly between 550 to 900 kilometers in altitude, but I think we should go a little higher and position ourselves at about 1,200 kilometers because this is above the belts with the highest space debris and atmospheric drag. Sure, that extra 400 to 600 kilometers will amount to an increase in cost, and sure, space debris is generally exaggerated in the headlines, but because we are actually building so large, we're basically volunteering to be the poster child for the next space traffic outrage cycle, and so it's my opinion that 1,200 kilometers is a good compromise between all these factors, giving us a cleaner story for licensing and insurance. And it's likely that if a station offering thousands of tons of low-cost mass and materials were in orbit right now, all these companies and agencies might adjust their planned inclinations and altitudes to take advantage of such an opportunity. So around 1,200 kilometers seems like something of a Goldilocks zone for this orbital depot. But altitude is only one scalar in the orbit. Inclination matters just as much because it sets the orbital plane, and changing orbital planes is extremely expensive in terms of delta V. It also dictates the Earth launch geometry and therefore the launch period. The first and most ideal choice would be a station in the lunar orbital plane due to the lack of required inclination changes. For low Earth orbit, however, this is not possible, as nodal precession would quickly swing the station out of the lunar orbital plane, revolving it around Earth's polar axis, which is highly inclined at about 23.5 degrees relative to the ecliptic, which is the plane in which the Earth's orbit occurs around the Sun and is the universal solar reference. Accepting that any transit plan must account for nodal precession, how do we get the best time average delta V savings? Because the target orbit precesses, it will periodically realign with the lunar orbital plane, so the obvious strategy is to choose an orbit whose nodal precession lines up with the moon's orbital plane as often as possible. The complication is that the moon's orbit also precesses under the influence of the sun, with a cycle period of roughly 18.6 years. When the lunar longitude of the ascending node is at 90 degrees, call that the start of the lunar nodal cycle, the target orbit needs an Earth inclination of about 28.59 degrees to periodically align with the lunar orbital plane. About 9.3 years later, when the lunar node is at 270 degrees, that required inclination shifts to about 18.3 degrees. Could a station continuously cycle between those inclinations over that period so we could minimize the mean inclination change work required to access the receiving station? Suppose the correction happens daily. Each day, as the station crosses the equator, a thruster performs a small normal burn. The required inclination change is only about 0.003 of a degree per day. At 1,200 kilometer altitude, where orbital speed is roughly 7.25 kilometers a second, that is about 0.38 meters a second of delta V required per day. That is very manageable, especially for a station constantly receiving incoming rocket pods, which should arrive with unused propellant margins, giving the station a nice reserve for orbital maneuvers and everyday station keeping, even if it's low-grade performance lunar ISRU-derived propellant. So by having the station undertake this slow and gradual inclination change to track the lunar nodal precession, we maximize the quantity of alignment periods it gets with the lunar orbital plane, and thus the average delta V required for a transiting rocket. And here I should note we're assuming a circular orbit for the time being, since it simplifies the planning of Rendezvous. But there is one more problem worth talking about first. Altitude also controls nodal precession and sets how fast the station's orbital plane naturally rotates around Earth. An exact 1,200 kilometer orbit would still work, but its precession would not line up cleanly with the lunar nodal cycle, so instead of treating 1,200 kilometers as an exact target, we treat it as the goal to aim for, and we search nearby altitudes for one whose nodal precession has a clean integer relationship with the moon's 18.6-year nodal cycle. This means the precession rates of either orbit work kind of like a clock, with the lunar precession being analogous to the hour hand and the target orbit precession being analogous to the minute hand. This is really useful in that it makes maneuver planning in accordance with the precession cycles easier. So to find this integer relationship, we wrote a MATLAB sweep over nearby circular LEO altitudes, calculated each orbit's nodal precession rate at the lunar aligning inclination, and looked for cases where an integer number of precession revolutions fit cleanly inside the moon's 18.6-year nodal cycle, and we got this beautiful graph. Though most of these are pointless, since we only really care about the point closest to 1,200 kilometers, which turned out to be 1,211.2 kilometers. So now we have a target altitude and inclination for the receiving station. But that still leaves one final problem: Rendezvous. Even if the incoming rocket pod reaches the correct orbit, the station is constantly moving around that orbit, so the pod still has to arrive at the right place at the right time. So we have solved the orbit geometry, but not the final timing phase between the pod and the depot. After much deliberation, we figured the simplest approach was just to have the rocket pods assume a parking orbit just above the orbit of the receiving station, where the rocket pods will simply wait for the correct orbital period alignment, allowing for a gentle Holman transfer and rendezvous. Basically, they just kind of fly above, wait for their time, and then dip down and rendezvous with the station. And if you think about it, this parked orbit, this queuing, essentially acts itself as a laydown yard. So the receiving station itself can devote less resources to storing these actual rocket pods. And it also acts as a supply chain buffer for fluctuations in the frequency of incoming rocket pods, which may come in bursts as a downstream effect of any number of reasons. But anyways, the point is this parking orbit allows the station to control the amount of mass it receives and can balance that with the amount of mass it exports to the market, thus allowing it to maintain something like supply chain homeostasis. To decide the altitude of our parking orbit above our 1211.2 kilometer receiving station, we sampled various orbits for the time and delta V required to Holman and rendezvous, but then decided to just draw a line at a flat 100 meters a second to give us a 1371.2 kilometer altitude parking orbit, where we'd only have to wait a maximum of 57.3 hours for the phasing to be right for rendezvous. So it's not like these would have to wait years, it's just a few days before their time comes. So technically that's our new target destination, not 1200 kilometers, not 1211.2 kilometers, but rather a lunar plane inclined 1371.2 kilometer altitude orbit. Though it's entirely dictated by the decisions that went into finding the 1211 kilometer orbit of the receiving station. So that's our destination. But what about the starting location? In the last video, we worked backwards using patched conics to find what looked like the best lunar launch location. And honestly, if all we had done was upgrade from patched conics to a more realistic multi-body simulation, the old location might have been good enough. It probably would have shifted somewhat, but not necessarily enough to throw the whole thing out. But we didn't just upgrade the physics, we also introduced multi-burn trajectories, which is a much bigger deal as that new degree of freedom changes the design space completely. So we had to re-find the starting location from scratch. This became phase 1 of the simulation work, what we called the allocation phase. The biggest variable we had to account for was timing. The moon is constantly moving around its orbit, so the lunar true anomaly, where the moon is when the launch begins, changes the geometry of the entire transfer. The target orbit is also precessing around Earth, so we also had to sample the target orbit's longitude of ascending node. Then we gave the optimizer the mass driver side variables it was allowed to play with: ejection velocity, lunar latitude and longitude, and the azimuth and elevation of the launch direction. But we constrained those ranges to be realistic. Ejection velocity was constrained between 2.3 and 3.5 kilometers a second. Longitude was constrained between -90 and 90 degrees, keeping us on the Earth-facing side of the moon, so communications can remain reliable. Azimuth was constrained between 0 and 180 degrees, meaning the mass driver only fires retrograde in this phase because that sheds Earth orbital energy on the way down to low Earth orbit, and elevation was capped at 0.5 degrees because the normal g-forces involved in anything more than that become untenable. We also did not allow for aerobraking. The rocket pods were not allowed to dip below 200 kilometers around Earth, both because skimming the highest thinnest part of the atmosphere is hard to model cleanly, and because accidental deorbiting is not a failure mode we want. The same 200 kilometer exclusion zone was applied around the moon because getting too close introduces extra perturbation messiness from lunar mass cons, which induce non-trivial perturbations for the moon as opposed to the Earth because the moon's much lower gravity. So phase 1 was basically a course search, sweep the major moving geometry, constrain the mass driver to plausible directions and velocities, and let particle swarm optimization look for regions where the required rocket delta V was low without creating ridiculous thrust to weight or timing penalties. If a pattern emerged, that region would become the fixed starting point for the more expensive phase 2 trajectory simulations. And we hoped a pattern would emerge. And what did we find? Well, lots of bugs. We had to restart twice over. But once it finally worked, we found not much of a clean pattern. There was a vague preference towards the lunar equatorial west around Oceanus Procellarum, but nothing like an obvious best area. There's this vague spot in the middle, but all of these transits were for when the lunar and target orbital planes were aligned, so it's not very representative. What this seems to show is that with multi-burn trajectories, mass driver locations may not be as sensitive as initially expected, and this appears to be because multi-burn smooths out the performance differences between sites, because the rocket pod has more opportunities to correct and shape the trajectory after the launch. Well, there is one recognizable pattern, and that is that the lunar poles are unfavorable places to put a mass driver, because the vehicle has to always fight larger inclination changes when leaving the lunar sphere of influence. But besides that, a lot of locations across the lunar west perform similarly in Delta V. So instead of getting one obvious answer, we got a rough region. The problem though is that for the next phase, which is the bulk of the work, we need one actual point. So we need to consider other factors of merit to determine placement outside of raw Delta V figures. There's a lot that could be debated here, but ultimately we chose to look at the lunar surface itself within this region, namely terrain, slope, and mineralogy. The logic was that the mass driver and the rocket pods and everything else has to be made out of resources, so which area has the most resources? This matters because every kilometer we avoid hauling raw material across the lunar surface is energy, equipment, and complexity we do not have to pay for. So to find these overlapping mineralogical sites, we took 9 remote sensing abundance maps from different papers, each estimating the distribution for a useful lunar material, and overlaid them to look for places where several useful materials appeared together. Then we added terrain flatness as another scoring factor by taking the gradient of a lunar height map, which gave us a rough picture of local slope, and then we ruled out anything that had too steep of an elevation. This matters as an additional consideration because flatter terrain reduces structural and logistical headaches for almost any kind of construction, and especially for giant solar farms and multi-kilometer long mass drivers on the moon. We then normalized these maps and built a non-linear optimization system that adjusted the threshold for each one. So for example, we could ask, only show me sites in the top 10 percentile for this material, for titanium or aluminum or thorium or whatever. The system then combined the maps and kept tweaking those thresholds to find regions that maximized the mean abundance of the useful materials while also favoring flatter terrain. And because when the only tool you have is a hammer, everything starts to look like a nail, we used particle swarm optimization again for this. This produced 8 candidate sites near the craters Plato, Kepler-T. Meyer, Frau Mauro, and Lalande. These should not be treated as the absolute best sites on the moon because the maps rely on imperfect remote sensing data, which has gaps that have been filled in with various methods. So these maps have artifacts, and it's important to note that our mineralogical understanding is severely limited at this point in history, so these optimal sites may very much change. But for now, working with what we've got, these locations do appear unusually rich in several useful materials at once. Out of these 8 sites, we chose to go with the one at Kepler Abundantia Tertia, or CAT for short, which sits near Kepler in the eastern middle region of Oceanus Procellarum because it has a lot of mineral richness overlap and is in our regional circle. But don't take this site as us declaring a final industrial capital of the moon. Rather, just take it as a defensible site good enough for the next phase of simulations. So now that we have a location to put the mass driver, we need to decide the launch orientation, the azimuth and elevation at which the mass driver rocket pods leave the mass driver relative to the lunar surface. Elevation is how high we tilt the mass driver upwards, so we can do stuff like gain altitude and prevent the payload being launched from immediately flying into the side of a moon mountain. But physics mostly makes the decision for us. Tiny angles become huge over kilometer scales. A 15-kilometer mass driver elevated by just 1 degree would end more than 260 meters above the lunar surface. That is massive structural overhead to maintain over many kilometers before even adding the converters, switching hardware, insulation, power distribution, and active thermal control systems that have to stay close to the launcher. And similar to this, a reoccurring idea I've seen a lot is to curve the mass driver upwards at the end, maybe by running it up a crater wall or some other natural ramp. But at orbital velocity speeds, even a gentle curve creates enormous vertical forces into the guideway. For example, a 20G mass driver launching a 300 kilogram payload is pushing it forward with about 60 kilonewtons of force. But if that payload is moving at even just 2 kilometers per second and we try to curve it upward through a 1 kilometer radius bend, The payload pushes downward into the guideway with about 1.2 meganewtons of force. That is equivalent to the weight of about 120 metric tons on Earth, roughly the weight of a fully loaded heavy freight rail car coming from a 300 kilogram payload. Except here it is not spread across a rail car and 8 wheels. It is acting as a moving vertical load through every coil section of a precision launcher that still has to remain aligned over kilometers. So the practical answer to elevation is none. Just to treat the mass driver as a horizontal piece of infrastructure, and fortunately the moon curves away about 3.7 times faster than Earth does, so we only need about 60 kilometers of cleared line of sight after the muzzle for the payload to be 1 kilometer above the lunar surface. Azimuth is the horizontal direction the mass driver fires in. So, for example, 0 degrees points toward lunar north, 90 degrees points east, 180 degrees points south, and so on. This matters because azimuth controls the initial plane and direction of motion of the rocket pod relative to the moon. And since the rocket pod is not trying to stay in lunar orbit, but escape the moon entirely, azimuth also helps control where it leaves the lunar sphere of influence, when it leaves, and what direction it is moving when it exits. That makes it extremely useful for setting up later maneuvers. To show this, we put together this animation. Here, we hold the mass driver location fixed at CAT and sweep the launch azimuth. Notice how even the same azimuths can converge into significantly different trajectories at different lunar true anomalies. That is because the moon is not moving through a perfectly simple circular orbit. Libration and orbital eccentricity change the geometry, so the same shot direction can lead to different departure conditions depending on when it is fired. Then, if we combine azimuth with ejection velocity, which is basically controlled by finely adjusting the electrical parameters of the mass driver, we get a much richer design space. We are no longer just choosing where to point the gun, we are choosing from a whole family of lunar exit trajectories. In our convention, an azimuth near 90 degrees gives us a more retrograde departure that is useful because it helps with in-plane maneuvering, especially lowering periapsis deeper into Earth's gravity well, but it still leaves the rocket pod with a lot of inclination change work to do later. The opposite trade-off exists near 0 or 180 degrees, where the mass driver is aimed toward the lunar poles. Those trajectories are better for setting up inclination changes, both through the rocket pod's own burns and through lunar gravity assists, but they are not as useful for the in-plane energy change we need to drop down toward low Earth orbit. So rather than choosing one extreme, we split the difference. We set the launcher azimuth to 45 degrees, then let the optimizer control ejection velocity to control how retrograde or highly inclined each departure becomes. This gives us a little more flexible family of exits instead of locking the whole system into one narrow trajectory type. And with that, we finally have all the pieces in place to run the main optimization we've been building up to. The good news is that because we invested so much time into setting up a good problem set, given all this context, the results themselves are much faster to explain. One reason the optimization took so long, other than our very poor programming skills, was the delta V cap. The allocation phase suggested that 4 kilometers per second was a reasonable upper limit, so we imposed that as a hard constraint and made the optimizer search only for trajectories that stayed below it. Most transits had no trouble staying under that limit, but some, namely the ones where precession created a large inclination mismatch, struggled more and had to be restarted several times, so the optimizer could search a different part of the solution space. But eventually we got every transit under 4 kilometers per second, which was very satisfying. Well, almost every transit. There was one that came in at 4.009 kilometers per second, but after watching it struggle for a long time, we kind of started feeling bad for it and decided that it was close enough to count, so we included it anyways. Poor little guy. Anyways, here's the results. These are so gorgeous. I wish we could sit here and look at every single one, but this video is already very long and we have more to discuss. Fortunately, Mel put together a video on his channel that looks at all of them back to back, so check that out if you want to see these in greater detail. I'll link it in the description. And then this beautiful plot shows the main transit parameters all together. The first indicates how much ejection velocity is required from the mass driver on a given transit. The second tells us how much rocket delta V a given transit required. The third tells us what our rocket thrust to weight ratio needs to be for that transit. And the fourth tells us how long each of our transits are going to take. And here is the distribution of these parameters. What these show, what all this hard work and time and energy went into, was the ability to say, with a reasonable degree of confidence, that to reach a 1,371.2 kilometer target orbit in low Earth orbit when launching anytime from CAT on the moon, regardless of the orbital conditions, a transiting rocket pod requires between 2.33 to 3 kilometers a second of ejection velocity from the mass driver, a delta V capability in the range of 3 to 4 kilometers a second, plus some propellant safety margin, maybe 5%, and the capacity to throttle up to a thrust-to-weight ratio of 4. So now we can finally attempt to answer the question from the beginning of this video. How small can we actually make the rocket pods? Remember, peak power is the issue. For example, a payload that masses in at 1 ton launched at 100 meters a second requires about 850 megawatts of peak power, with roughly 12 seconds spent above 425 megawatts on the way to peak. This is very high, especially for Lunar-made switches and hardware, so we want to reduce peak power. And recall that of the two main ways to reduce peak power, we decided that lowering the mass of the rocket pod was more attractive than lowering acceleration, because if we lower acceleration, we have to increase the launcher length. But lowering the pod mass allows us to lower the mass driver size and power, but we lose out on economics as we would have lower throughput. But we can combat this by simply keeping the same sized launcher, so the launcher is not sized for any single shot, but rather for some amount of mass per hour for throughput. And this is dictated by thermal cadence, the steady state firing temp, and by lowering the mass of the rocket pods and firing smaller pods at a more rapid rate, so we have the same economics, we are able to lower peak power without increasing the size of the launcher or anything else. For example, a 1 ton per hour system could launch one 1 ton pod once an hour, or 10 100 kilogram pods every hour, one every 6 minutes. The output is the same, thermal is the same, and therefore the mass driver size remains the same, but each individual shot has 1/10 the peak power demand. So by lowering the mass of the rocket pods, we relax the hardest part of the mass driver. But that only works up to a point. The pod still needs a rocket motor, structure, guidance, power, thermal, margin, fairing, and the armature that couples it to the launcher. None of that scales down to 0. So the question is, what is the limit? If smaller is better, how small can we actually go? And now, from the simulations, we have the two numbers we needed. Roughly 4 kilometers per second of delta V, and a thrust-to-weight requirement of 4 as well. These are non-trivial delta V and thrust-to-weight figures, but they are not outside the reasonable bounds of application for something like a potentially radically inexpensive aluminum oxygen thruster operating at an ISP of something like 230 seconds. And it's worth noting that this is the most we will need, as many flights were under this amount. But it's worth noting that we might want to design for the worst case regardless, and that a good strategy may be that if the transit requires less delta V, we should just put more cargo on it, so we don't have to make a more complex rocket that can tolerate different propellant mass fractions. I.e., less delta V means we should increase the dry mass, not lower the wet mass. So we just design every pod to be the same delta V and vary the payload rather than varying the design, so we can achieve manufacturing standardization and scale. Anyway, with these figures and an assumed specific impulse of 230 seconds, the rocket equation gives a mass ratio of about 5.9. That means roughly 83% of the wet pod mass has to be propellant, leaving only 17% for everything else: the dry rocket hardware and the useful payload. So then, how much of that 17% is structural overhead, what we can call dry mass, and how much is left for payload? How do we divide this 17? To estimate that, we looked across a range of real rocket motors, from hobby motors up through small aerospace solid motors, larger star motors, and finally Falcon 9 as a rough high-end comparison using this big brochure from Northrop Grumman and this hobby rocket models page, and we put together this data table which we then plotted into a graph, and look, there's a pattern. Very small motors of a few kilogram are pretty structurally inefficient. The hardware overhead takes up a huge fraction of the vehicle, but as the motors get larger, the inert fraction becomes much smaller as economies of scale take hold, But then the rate of gains fall off and the trend plateaus around maybe 500 kilograms, but by that point their inert mass fractions are around 6 to 8%. There is an important caveat though, as many of these entries are motor only numbers, so they do not include the other structural things. So if a motor has a 6% inert fraction, the full rocket pod is not really 6%, it might be more like 8 to 10%. But anyways, for this first order sizing, I think we can defensively say that a 500 kilogram wet rocket pod is a reasonable baseline and would give us something like a 7% payload margin, with 10% being the structural overhead dry mass. So we're dividing that 7% with 10% being the structure and 7% being left for whatever payload we're putting in it. Using the same acceleration and muzzle velocity as before, that would require about 423 megawatts of peak power, with an average power of about 212 megawatts during the 25.4 second launch, meaning the system spends about 12.7 seconds above 211 megawatts on its way to peak. At one launch every 3 minutes, that works out to be about 30 megawatts averaged over time. This is still significant, but much better than the 850 megawatts peak required for the 1-ton launcher. And if we need less, we can go even smaller, though you'll be eating into your payload margin, but that might actually be okay, and you might even decide you don't really need a payload, you're more interested in the material that the rocket pods themselves are made out of. But anyways, at 500 kilograms of wet mass, 83% propellant means we need about 415 kilograms of propellant, and that leaves about 85 kilograms for everything else. If we allocate roughly 50 kilograms to dry pod hardware, then about 35 kilograms remain for payload. That sounds small, but 35 kilograms every 3 minutes is still 700 kilograms per hour, or about 16.8 tons per day. And recall that the rocket pod itself is usable mass, not just its dedicated payload fraction. The total rocket pod is 500 kilograms, full of propellant and fuel, but the dry mass, just the spent casing plus whatever payload it has, would have a total mass of 85 kilograms. So if the total useful mass delivered to orbit is arguably the full 85 kilograms, not just the 35 kilograms of flexible payload, then counting the spent casings as the true exported mass, at one pod every 3 minutes, that works out to about 1.7 tons per hour, or nearly 41 tons per day. That 35 kilograms is just what we might consider dynamic or freedom of choice mass. It could be anything: electronics, fuel, wafers, rocks, thorium, plutonium, whatever. And if we only care about aluminum and steel and fuel, and don't need a payload margin, then we can shrink it even further, thus lowering peak power even more. So all this work shows us the scale of a continuous access mass driver and what is required to make it work, what metrics we need to achieve. What remains are the big questions regarding in situ resource utilization and manufacturing, how to actually build it. Answering these questions is the work we have to do now. But now we know that work will not be done in vain. There is a path off this rock. There is a future in which material is cast along cis-lunar space at a frequency and throughput comparable to the railways of Earth today, and perhaps even greater. Perhaps thousands, maybe eventually tens of thousands of tons of mass could be exported to low Earth orbit every day for 2, perhaps 3 orders of magnitude less cost than a single rocket launch today. And then we build behemoths. We opened this video with a question. What is the smallest near-term mass driver we could actually build on the moon? How long is it? How many tons does it weigh? What does it take to actually build it? Unfortunately, this video has already become far too long to answer all of that here. But now, for the first time, we actually have the baselines needed to do it. We know the destination, the launch site, the required ejection velocity, the rocket delta V, the thrust to weight ratio, and a defensible first estimate for pod size and throughput. So in the next video, we are going to take everything we established here and work backwards into the mass driver itself. Though while you wait, I want to genuinely encourage you to try answering those questions yourself. Take these numbers, build a model, make assumptions, run a simulation, and see what you find. We usually think of simulations as tools for modeling specific processes, but a better perspective is that simulations are a remarkably effective way to learn about a problem itself. They give us a picture into what the problems actually are. It is all well and good to have an idea, but ideas are now cheap. We live in an age where communication is saturated with confident hand-waving, where concepts are easy to generate, easy to dress up, and very difficult to verify. So this is a call to anyone with ideas about space, and especially to anyone interested in our industrial future beyond the Earth. Start building simulations. Do not let an algorithm, a pitch deck, or whoever happens to have the loudspeaker decide what you think is possible. Follow relevant technical documentation, read papers, make simulations and build diagrams and even animations to check your work. The computational power available to you is enormous, probably more than you realize. And once you actually understand the problem, you may find yourself in genuinely novel territory, asking questions no one has asked before, because almost no one has looked closely enough to see them. This is not a trivial pursuit, it is a deeply meaningful one. Humanity's future in this dangerous, unfamiliar, and extraordinary environment calls many of our terrestrial assumptions into question. The rules we have grown used to about energy, structure, land, distance, scarcity, and material abundance may not hold forever as we move out into space. Maybe one day megawatts may be freely afforded to each of us individually to do whatever we want with. One day we may be able to buy centrifuged land by the square kilometer on moderate budgets in space as individuals. But that future cannot be left only to institutions, investors, algorithms, or whoever happens to control the loudspeaker. Ordinary people need to understand it too. We need to understand the constraints, the opportunities, the dangers, and the trade-offs before we can meaningfully choose what kind of future we want. Because space will not automatically make us wiser. It will only give us a larger arena in which to act. It is up to us to learn how to use it for better rather than worse. It does not matter what tools you use. It does not matter whether you are a good programmer yet. You might be a high-level Python person, someone who works in C and inline assembly, or someone building physical models on an actual table. The point is not to begin perfectly, the point is to begin. Take the first step, make a crude version, see what breaks, then make it better. For repetition is what truly brings understanding, not raw intelligence or innate skill. The master has failed more times than the student has tried. Ideas are always cheap. It is the work that follows that gives them value. If you're unfamiliar with the process, the resources are here. We have the internet, Google Scholar, the archive, public datasets, open source code, and an endless wellspring of ideas to study for free. You can find tutorials on YouTube that rival university lectures. You have access to the tools. You have access to the knowledge. Now it is time to just start. And once you have your results, join the Anthrofuturism Discord and present your findings, where I'm sure a great many salty nerds will be eager to argue over every assumption, equation, and tiny detail.